Accuracy and precision is something that we're going to use within lab quite a bit. So accuracy is a measure of how close a measurement comes to the actual or true value of whatever is measured. So if you ever see this triple equal sign, that means that is a definition. So with accuracy, it will depend on the person measuring. And to evaluate accuracy, we're going to use the percent error formula. The percent error formula is right here. That is the accepted minus the experimental all over the accepted times 100. And then that does give you your percent error. And so that basically tells you how good of a job you did, right? And so you're hoping to not have a very large percent error. You're hoping to have a very small percent error. Now, precision is a measure of how close a series of measurements are to one another. So this will depend on the measuring tool and the number of significant figures that you have. So to evaluate precision, we're going to use the deviation formula. The deviation formula is also an absolute value. And notice it's going to be your measured value minus your average value. We're not going to calculate this one quite as much. I just want you to be aware of it. Is to evaluate precision, we're using deviation. To evaluate accuracy, we're going to use the percent error formula. So here's just a quick visual. So in class, I would love for you to be highly accurate and highly precise. So if you look here, and if you're aiming for that target, that would be amazing. But realistically, with the equipment we have, and you're new to a lot of the lab stuff, I'm guessing we're going to get low accuracy, but hopefully high precision because of the equipment we have. Hopefully you're consistent in your abilities. What I would like to not see in lab is low accuracy, low precision, that you're just kind of all over the place. And the other thing I would also prefer not to see is that one person in your lab group can do it, but nobody else can. I would like to see some consistency within a lab group. So I think like the dartboard analogy is a really easy way to look at that high accuracy and or just comparing accuracy and precision in general. So I put this in here just to give you an idea using words explaining accuracy versus precision and looking at a data table. I'm not going to read this to you, but I would suggest looking at it a little bit closely to kind of get familiar on, what is accurate, what is precise. So I do have this question here, and I meant to give this to you before, but the percent yield equation is experimental value divided by the accepted value times 100. So we're going to go ahead and do this practice problem. So what is the percent yield of an experiment if you calculated that you should be able to form 1.92 grams of sodium chloride, but when you weighed the sample, it weighed 1.96 grams. Okay, so our experimental value was 1.96. Our accepted value is 1.92 times 100. And when I solve it out, I find it to be 102%. Now, you really shouldn't be above 100. So by having more than 100%, my guess is there's some kind of source of error. Okay. And as we do labs and things, I want you to think about what source of error is part of this lab. For example, was this sample truly dry? If it wasn't dry, was it too wet then? In which case you would have a higher percent error. So whenever we do anything in class, I want you to think about, okay, is this accurate? What is contributing to my results not being what I would expect? Now in these next two slides, I wanted to point out that in the I do, we do, you do slides, there are QR codes of somebody else solving these, and I highly recommend that for practice. So that's on both of these. Now, I thought we could do this problem together. These students were asked to find the mass of 10 milliliters of ethanol. So we have Ash, Blake, and Casey. And we're looking at the data to determine if they're accurate, precise, both, or neither. So looking at Ash's data, we have 7.90, 7.91, and 7.92. I am comparing this to 7.89. To me, that seems pretty close to 7.89. So my guess is I would say that they are accurate. Those are pretty darn close together, so I would say they're precise. So I'd probably say that that is both. Let's look at Casey's data next. I'm going to jump a little bit. I look at Casey's data. We have 6.89, 10.89, and 5.89. I feel like Casey's all over the place. So she's not precise and she's not accurate. So she's neither. Now let's look at Blake. Blake has this one that's pretty close, but the 7.01 and 7.21, we're in the sevens. So I feel like this is kind of a gray area. It's kind of a little bit of accuracy and a little bit of precision, but not amazing. So there is going to be sometimes a gray area, and you could always substantiate that with evidence. So on an exam, I would try to make it much more obvious than Blake's situation. I'd make it closer to an Ash or a Casey to make it more obvious when you have to answer the questions. Then we're going to calculate the percent error for Casey's first trial. So if you recall, that equation is accepted minus experimental all over accepted. And we're going to multiply by 100%. Okay, so if we do this, my accepted value is 7.89. That's going to be given to me here. I'm going to subtract that 6.89 of the experimental all over accepted. Let's see what you get. So keep in mind your percent error should always be positive because of that absolute value. So I found it to be 12.7%, which is actually not as awful as I would think, but they could definitely do better. So here's some other questions that you can work on your own. I have embedded a key at the end, but I just want you to know there's lots and lots of practice of all of these. And so I will always embed these I do, we do, you do questions and then the answer key. I have also added additional practice videos for you to help you understand this.